All right, so we're going to introduce a new concept here. It's writing radicals as rational exponents. Okay, this is really useful to us because a lot of times when we're simplifying more complicated expressions involving radicals. Radicals are a little clumsy. Sometimes it's hard to do when it's in radical form, but if we convert those to exponential form, then we can use all those properties of exponents that you know and love that we reviewed earlier in the year. And it makes the whole process a little bit easier, right? So first of all, let's get some definitions here. So how do we write a radical an as an exponent? Okay, it becomes a fractional or a rational exponent. So if I want to turn the nth root of a, now n just means whatever the index is. So if it's a square root, it would be a 2. If it's a cube root, n would be a 3, etc. So if we have the nth root of some radicand a, where a just represents whatever's inside the radical, right? Then the way we do that is we write it as a to the power of 1 over n. Okay, so notice the pattern here. Notice that whatever the index of the radical is ends up as the denominator of the fraction. Okay, write it as a fractional exponent that way. If we want to do something like, so for example, let's just do one of these really quick. Let's get a little practice in. So how would I write 24 as a radical, or not 24, that top example as a radical? What is it? Okay, no, but you're multiplying 24 times 1/3, right? Is that what that's telling you to do? No, if I was multiplying, it would say 1/3 right next to the 24, right? Or with a time sign or something, right? So you got to think about the operation. That's not multiplying. What are we doing there? If I raise that up to an exponent, what do we call that? What's the verb that goes with that? We know how to say, like, if it were 1/3 times 24, well, we multiply. That's the verb. What are you doing here? Okay, good. You're raising 24 to a power. So you could say 24 raised to the power of 1/3. Or you could say another, like the kind of the more mathy word we use is exponentiate, right? We're exponentiating 24 with the exponent 1/3, but we just say raise it to that power, right? So you don't multiply when you raise things to power, right? So what's this equal to? That's not 8. We're not multiplying. What do we do there? It's 16. We're exponentiating, right? So we got to raise something to a power. Okay, uh, but the point here is we want to write that as a radical so we know what to do with it. How would I write that as a radical? What's my pattern? A to the 1 over n is equal to the nth root of a. But how, but how 3 radical, you're telling me I want you guys to start to be a little more careful about how you're saying this stuff. I know you're thinking the right thing. Go ahead, Marie. There you go. Yeah, cube root of 24. Or if you forget it's a cube, you can say the third root, right? But if we say 3 radical, that means 3 times square root. That's not what you want to do, right? You're trying to do a different kind of root. The kind of root you're specifying is a cube root because of this guy, right? This is going to end up being the index of the radical. Okay, so we end up with then that the 3 goes there, right? It's a cube root of 24. Okay, and now we could, we've done a lot of stuff like this. We could simplify that radical by just making a factor tree, right? So what am I trying to do? What's the saying that would go with simplifying a cube root? Okay, I'm going to factor it, but once I do that, what's the whole point? We talked about going out and staying in kind of stuff, right? Triples go out, good, and everything else stays in, right? Triples go out, everything else stays in. So we'd want to make a factor tree out of that 24. And we'd probably break that down. And ideally, we want to break it into a perfect cube and another number, which we could do. We could make that an 8 and a 3, and then we could skip a step and just make branches to 3 2s from the 8, right? And then over here we get a 3. So what's the outcome then? Well, we get a couple of 2s, or sorry, triple 2s and a single 3, right? So when we write this thing out, what goes out? Well, 2. We said triples go out, right? So 2 goes out, everything else stays in, so I've only got one thing inside, it's a 3. Okay, make sense? Give me 1 to 5 on that. Everybody good with that? Okay. All right, so now let's backtrack for a second and let's look at the next level of this. Well, what if we want to do something like we want to convert the nth root of a power? So now inside the radicand, I've got an a to the power of m, and I'm taking that whole thing, taking the nth root of that whole thing, right? Then what happens? Well, just like before, the index of the radical goes in the denominator, but now whatever the exponent is that goes with the power, right? That's going on the top. We did the same thing up here. We just didn't know about it. There was just a 1 there, right? A is the same thing as a to the 1. Everybody get that? Okay, now this is equivalent to, I'm going to show you one other thing. These two expressions mean the same thing, right? We could either do the nth root of the quantity a to the m. So in this case, if I wanted to introduce some little parentheses, they'd be there, right? So in this case, the a to the m is inside of the radical. That's the very same thing as doing that. What's the difference? Well, it just depends. Are you going to take the root first and then exponentiate? Or are you going to exponentiate the a and then take the root? The outcome is the same either way. So they both would be written as a to the m over n, either one. Usually that first one's a little bit easier to write, to keep the exponent inside the radical. Then it's less confusing visually. So usually we just go with that one, right? But they both mean the same thing. Okay, so let's practice. How about next one here? 27 to the 2/3. Okay, so what are my options here? How could I write that, Andre? What's one way I could write that as a radical? How do you say it again? The like the cube root, yeah. There you go. So that's one way we could do it, right? We could do a cube root of 27 squared. And if you forget it's a cube root, you can just say a third root. Doesn't matter. Just like we could say, we always say square root. We're really used to that, but it's really a second root. But no one would ever say second root. We just say square root because we're used to it. So then, whoops. So what goes where? Okay, so the 3 that was on the bottom goes there. The 2 that was in the top of our fraction goes there, right? Okay, that's good. That's how we could write that. What's the other way of writing that? What's the other option? What do you got? Okay, we could cube root it first. And then square it on the outside. Okay, it's easier to write the top one, but when you were actually evaluating a number this way, we're not dealing with any variables. We're just trying to get a number outcome here. One of these is way easier than the other one. Let's look at both of them and you tell me which one is easier. Okay, this one would be the same thing as saying the cube root of 27 squared. We could do it, right, making a factor tree. We'll come back to that one, maybe. How about the bottom one? What's the cube root of 27? 3. Yeah. So this is equal to 3 squared. Well, that's pretty easy. What's that? So which way is easier? Yeah. Now let's think about why that is, right? Just think about, there's two steps to this process, right? If I'm taking a number to a fractional power, uh, when I take a root of a number, is the result small or big? Like if I take a cube root of 8, that's small, right? If I take 8, if I cube 8, it's really big, right? When I take numbers to powers, they grow really fast and they get really big. When I take roots, they generally get small, right? So what would we rather do? Would we rather exponentiate first, so the middle step is we've got a big number that I've got to take a root of? Or would we rather take the root first and get a small number that we exponentiate? Second one, right? So the moral of the story is, when I'm taking a number to a fractional exponent, do the denominator part first, do the root part first, and then take it to a power. Now that doesn't mean it's not easier to write it this way. Like when we're dealing with exponents, we'll write it that way. It's just easier, right? To have the exponent on the inside. But when we're actually doing the process of simplifying a number, you could do this all in your head too. You really could, right? You can just think of this, cube root of 27. Okay, I know that's 3 squared, 9, done, boom. Okay, no big deal. Try one of these. Just practice this. I'll give you another one. I'll show you how easy this is. You guys can get this. What is, in fact, why don't you go to the boards? Quickly, just zip to the boards and try this one. Yeah, yeah. Okay, so 8 to the 5/3, go. Okay, but you got to have a radical there, right? That 3, what's that 3 doing? That 3 is the index of a radical. And then the 3 would go, 3 goes there. Yeah, see what I'm saying? But you're right, but you're taking it to the 5th. No, because look what you did. Is that what you were supposed to do? Is it 2 times 5? Is that what that means when you see something like that?
Oh no, it's 2.
It's 2 times itself, so there's 5 2's multiplied together, right?
Yeah.
Okay. Close.
Oh, wait,
2.
no, it's 32.
There you go. Yep. Yep. Good. Good. Good, good. All right. Excellent. Race the boards, grab a seat. Okay, so you got it. Everybody was on the right track here. So everybody was doing the right thing. They were cube rooting the 8 first and then taking that whole thing to the 5th. Okay, good. Well, that just gives us cube root of 8 is 2. 2 to the 5th is 32. Now, how can we get that fast? Oops, not 2 to the 32. What am I doing? 2 to the 5th equals 32. 2 to the 5th you can do pretty fast, right? Here's how you can do it fast. We can, what's 2 cubed? Duh. It's right there, right? 2 cubed is 8. So then all we got to do is multiply that by another 2 squared. So here's the mental math we could do on this. 2 to the 5th equals 2 cubed times 2 squared, right? Everybody see that? Because what's our property? If I multiply like bases, don't I add the exponents, right? So we just get our 8 times another 4, which is 32. You didn't probably need it so much with 2's, but if the base had been something bigger than a 2, that might have been kind of handy to do, right? Something like that. Just use those properties of exponents. Okay. What about something like the top one here? Talk to me about that. What am I going to do there? I want to simplify that. It looks terrible, but it's no big deal, really. You got X's and Y's and Z's, but that's all right. I mean, they're going to end up on our answer. Who cares? Talk to me about that. What do you think? What do I do with the 12? Distribute it. Okay, let's talk about that. So that means if I distribute it, what you're saying is, let's take a simple example. This is oftentimes a really good thing to do in math. If you're not sure about something, you want to test out an idea. Pick a really easy example instead of something looking complicated like that. Pick an example with numbers. Like, what if I wanted to do something like 3 times the quantity 2 plus 4 squared? So you're saying I could distribute the 3, right? That's what you're suggesting. I can distribute over a quantity when I've got an exponent. Okay, so what would that give me then? That would give me 6 plus 12 squared. 6 plus 12 is 18. 18 squared is a big number. What is 18 squared? Oh my goodness. 12 times 18. 18 squared. Well, we could do that. 20 squared is 400 minus 39 would be 61 minus 18, 19, 37, 31. So it'd be 324. Exactly. So is that the right answer? Well, if we follow PEMDAS with numbers, we know what we're supposed to do. We work inside parentheses first. So 6 squared is 36 times 3. No, that's 108, right? So we got the wrong answer. You can't do that. The actual answer is 108. So what's the moral of the story? Yeah, you can't distribute if I've got a power there, because that's violating order of operations, right? What's order of operations tell us to do? We have to exponentiate before we multiply. So can't do that. We can only distribute if there's no exponent. So what happens with the 12 then? Nothing. It stays out front. It's an outside number, isn't it? Right? This whole part right here is going to turn in, if I've got some quantity to a fractional exponent, that's going to end up looking like a radical, right? Fractional exponents convert to radicals. So let's deal with that whole part first. What's that going to become? How am I going to say that whole thing? Veronica, what am I going to do with that? I've got some quantity. It looks complicated, but who cares? I've got some quantity to the 7/3 or the 3/7. What's the 3/7 part? Well, okay, so like if I've got something to the 3/7, what's the bottom part of that fractional exponent telling me? So I know I'm going to write that blue part as a radical, right? I know it's going to end up being a radical. I guess I want to know what number is going there. 7, exactly. Okay, and then what's the 3 doing? What's the 3 doing? It looks complicated because I've got this whole big thing here, but remember that when we're in math, when we encapsulate things in parentheses, what does that mean? If I'm encapsulating stuff in parentheses, it means I'm grouping it and treating it as one packet, right? So I've got all this stuff in a packet, so I can just leave that as a packet. What am I doing to that? What's the 3 telling me I'm doing to that packet? Cubing it. Exactly, right? That's the exponent. So the 3 is going there, and the packet is just, well, I guess it looks kind of complicated when you write it, but when we package it up into just one quantity, that's all right. We just treat the whole thing as one individual entity, right? Okay. So that's why when we use language in math, you hear me talk about the quantity a lot, what do I mean by that? Well, I mean the stuff that's grouped together in parentheses. Doesn't even have to be parentheses, could be a bracket. Anything that groups stuff creates a quantity in math, okay? And then what happens to the 12, did we say? Stays out front. That's an outside number, right? It's outside of the radical that we're creating when we have that 1/7 in our, right? So it just stays out there. Okay, make sense? All right, now compare that to this guy. Okay, this is a little different, right? Now we got something else going on here. We've got a negative exponent. So we have to remind ourselves about what the heck we do with negative exponents. Who can remember? What's our property here? If I have a to the negative n, how do I rewrite that with a positive exponent? You mean 1 over that, you mean? Yeah, okay, good. So how did we talk about that ages ago when we reviewed properties of exponents? Remember what I told you guys, we're always going to think about this as a negative exponent in the top of a fraction converts to a positive exponent in the bottom, and vice versa. If I had a negative exponent in the bottom, we boot it up to the top as a positive exponent. It just always pushes the power to the other part of the fraction to make the exponent positive. That's really all a negative sign does in an exponent. Okay, so there's our property. Okay, so then the negative part is doing what? Not very much, right? Whoops. The negative sign's not doing a whole heck of a lot here. All it's doing is putting this whole thing on the bottom, right? That's what the negative part does. What about the rest of it? How do I write the rest of it? Well, I guess for now, let's just write it as an exponent, and then we'll convert it later.
Q root of 31x or the 4. I'm doing cubes.
Right, so let's not even worry about the radical yet. Let's just, like, what does just that one property do? Let's break this down into really small steps, bite-sized pieces here. All we did here was deal with the fact that we have a negative exponent. What did that do? Yeah, so on the bottom, I've got what?
31x.
Good, the quantity 30. You see why I want to say the quantity now? Because it means it's grouped, right? The quantity 31x, so that one packet of stuff, what am I doing with it? To the what? To the 1/4, exactly, to the positive 1/4. So then now all we've got to do is just write that bottom stuff with a radical. That's no big deal. So I get 1 over what? The 4th root, good, over the 4th root of what? 31x. There you go, no big deal, right? So this time the 31's an inside number, isn't it? Because it was inside the quantity that was being exponentiated. See the difference there? Okay. All right. So next issue then. Well, this is easy. Now we're just going to reverse the process here. So now I just want you to write that top example. Yeah. Write that top example as using rational exponents. Starting off as a radical, write it using exponents instead. So treasure, how are we going to do that? What am I going to do? I'm going to have a radical there of some kind. What number's going there? Oh, sorry, it's already a radical. Sorry, that's not what we're doing. We're writing it as x to a power. A fractional power. There you, hold it, is it 6 over 7 over 6? Exactly. And the way we remember that, it's an easy, yeah, I know you were thinking the right thing. Because we know that the radical, the index of the radical, that's the part that always goes on the bottom. So the rest of it's pretty easy to track then. That means the 7 goes on top. Good. Okay. And if we wanted to do something like this bottom guy, what am I going to do there? Say it again.
5 to the power of 3.
Exactly. There's the beauty of using rational exponents. How did he get that? Kenny's a step ahead here. See, this is why it's so valuable to write this stuff. That looks complicated, right? That looks like we've got to take a fifth or 5 to the 6, that's an enormous number, right? And then square root that thing, right? But if we write this using rational exponents, the answer is obvious. So what's going to be the power? I'm going to have a fractional exponent in my power. What goes on the bottom? What goes on the top? 2 goes where? Bottom. 6 goes on the top, right? And again, let's track those. That's where the 2's coming from. That's where the 6 is coming from. But now that we've written that as an exponent, well, how could I simplify that exponent? 3. 6 over 2 is just 3, exactly. And 5 cubed, that's easy. That's just 125. So we got it, right? So rational exponents are our friends. Like converting stuff, and oftentimes like there'll be problems that it'll say at the end, it'll say, okay, write your answer as a radical, darn it. You gotta, because that's kind of clumsy. But a lot of times questions will ask you that. But what you could do is you could do all your work as using exponents, right? You're going to convert, you're going to move sideways, make a lateral move to convert everything to rational exponents. Take advantage of those easy properties of exponents, get an answer, then just convert it back to radicals for the answer. Yep. Yeah. Okay. Yeah. Absolutely. So take the next one. What are we going to do there? Yeah, it's going to be x to the 12 thirds, which just becomes x to the fourth. Way easier, right? Okay. All right. That'd be your answer. Yeah, that's simplified. Absolutely. Instead of doing the radicals? Oh, yeah, that's good until you need to know how to do the other stuff, and then you've never done it, you know? Okay, so I think this is probably, yeah, that's our last one for today. Okay. So what do you think? What am I going to do there? You can't. And I mean, I can't distribute the 12 because that'd be kind of weird, like distributing something to a index of a radical. Does that feel solid, like a solid move, even to you? Not really, right, Nolan? You suggested it, but I think you were spitballing before you'd had a chance to really think about it. What would you do? Okay. No, but let's take it in pieces. Kenny, what's your idea?
Could I do x and then I got 2/3 for its power, and then could I do 12/1 and simplify like?
Okay, good. Okay, so let's first of all let's just take this in pieces, right? So we're gonna use order of operations. So first we're gonna just move, do everything inside the parentheses and the grouping symbols. Okay, so let's do that. If we just take this part right here, oh whoops, that's not what I want to do. This is what I want to do. If I take this part, that's just becoming x to what fraction, everybody? 2/3, right? Okay, x to the 2/3 to the 12th. Well, we have a property for that. You guys all know this property. If I take a power to a power, what do I do to the exponents? Multiply, right? Yeah. So we get a to the m times n. We add them if we're multiplying like bases, right? That's different. Okay, so then all we got to do here.
That's what I meant to begin with. Like, no, that's serious. I meant to distribute the 12 to the 3 to 2.
Oh, so
But you can't. You're not distributing to the 12 to the 3 and the 2. You get x to the 2/3 times 12, which we would write as a fraction.
That's what I said.
Yeah.
That's what I said. That's what I said.
I said it before.
Okay, so then what do we get? If I do 2/3 times 12, what is that?
To the 8. It's
8.
Clearly, I'm a step behind too.
Right? And you can do it two ways. Like if you just multiply straight across, you get 24/3, which is just 8, right? Okay, so x to the 8th. Good? All right. You guys got to get going on this assignment, get a little practice.